Hello everyone, welcome back. In this particular video, we're going to start talking about the intramolecular aldol reaction. This is the aldol reaction that happens within the same molecule. And so what it requires is a compound that contains more than one carbonyl group. So you need at least two carbonyl groups in the molecule for this intramolecular aldol reaction to happen. So for the purpose of the example, to walk you through the reaction and through the mechanism of this process, I've chosen this molecule here, which, as you can notice, has two carbonyl groups. There is a ketone and there is an aldehyde functional group within the same molecule. So there are two carbonyl groups within the same molecule. And when you heat this molecule with base, it is converted into this ring compound. It's a six-membered ring compound. Now, if you look at the compound that we made here, this compound does look like an alpha-beta unsaturated ketone. Okay, it's an alpha-beta unsaturated ketone. So with respect to that carbonyl group, this is alpha and that's beta. So it is actually an alpha beta unsaturated carbonyl compound. So that's what tells us that this is an aldol condensation reaction, because alpha beta unsaturated ketones or carbonyl compounds, these are products from an aldol condensation. That's how we get this product. Now, to start working on it, it is always useful to number your compound because that helps you see what's happening in the reaction. So I'm going to number this compound. This is not IUPAC numbering, but just some numbering for me to keep track of the carbons in this molecule. I'm going to say this molecule here has 3, 4, 5, and 6 carbons in it. And if I use a similar sort of numbering, when I translate it to the product, I think what we're looking at here is 1, 2, 3, 4, 5, and 6. That's what we're looking at in the product. But we'll talk about how do we get to that number. Okay, but we are talking about the alpha carbon chemistry. This is a reaction that's happening under basic conditions. So the mechanism of this reaction is going to follow the mechanism of an aldol reaction under basic conditions. Now, for this particular molecule, if you were to think about the number of alpha carbons that are present in the molecule, we would have to say that this compound here has 3 alpha carbons. Okay, 3 alpha carbons because 1 is alpha, 3 is alpha, and then 5 is also alpha. And all of these alpha carbons have alpha hydrogens on them. So in principle, any of those alpha carbons can form an enolate under these conditions. So let's start working on the mechanism. So we have our compound here, and there is alpha here, there's alpha here, and in fact, there's alpha here. So when we react this compound with base, and in fact, recognize that the enol is not favored under these equilibrium conditions when we are using hydroxide as a base. So we will have some enol formation. But in principle here, we can have 3 different enolates that are possible. Okay, enolates, sorry, under basic conditions, 3 different enolates that are possible. So the base can deprotonate this first alpha hydrogen. And if that happens, the electrons from there would go here and the double bond would open up. And so that would give us one enolate. And so the enolate that we're looking at is this one here. So we have 1, 4, 5, and 6. So that's one possibility for an enolate. We're going to call this enolate 1. Okay, let's call this enolate 1. A second possibility, or in fact, all of these are happening in equilibrium. So all of these enolates would be formed. Okay, so the second possibility here is that the base deprotonates this other alpha carbon, the second alpha carbon that's here. And if that happens, then the electrons from there go to this bond and the double bond would still open up. And so that would give us the second enolate. It's going to have a double bond here. Then we have carbon, fifth carbon, sixth carbon, aldehyde. Okay. So again, if we follow the numbering, notice that we can make the enolate at carbon 1, or we can make the enolate at carbon 3. And then we have our third possibility, which is that the base deprotonates this third alpha hydrogen, in which case that electron pair would go there, and we are going to make a different enolate. Okay, so this was our enolate 2. And we have the third possibility for an enolate, which is going to be this one here. Okay, that's our third possibility for an enolate. So we have 1, 2, 3, 4, 5, and 6. So all 3 of these enolates can indeed form when this compound is reacted with a base. But what matters is what next, what could potentially happen after the enolate formation. So if we look at these enolates, because we have a compound with 2 carbonyl groups in it, once we make the enolate, we have a nucleophile in the molecule. This carbon is nucleophilic, the alpha carbon. In the second enolate, the third carbon is nucleophilic. And for this third enolate, the fifth carbon is nucleophilic. They are all nucleophilic because enolates are nucleophilic at the alpha carbon. Now, so if there is a nucleophile, there are also electrophiles within the same molecule. If you look at the first enolate, carbon 6 here, this is electrophilic. For the second enolate, carbon 6, this is still electrophilic. Okay, sorry, and this is enolate 2, and we actually have enolate 3 here. And for the third enolate, carbon 2 is electrophilic. So we have a nucleophile and we have an electrophilic carbon within the same molecule right now, or within the same species here. And so what's possible is that the enolate can attack. So for the first enolate here, the oxygen lone pair comes down. So that electron push is very similar to what we've been doing so far for all the alpha carbon chemistry that involves enolates. The lone pair on the oxygen comes down to form a double bond. And the pi bond here, which is the enolate, part of the enolate, opens up and it's going to go and attack carbon 6 and then open up the double bond here. Okay, that's what's going to happen with the first enolate. For the second enolate, the double bond can come down and the pi bond can open up and go attack carbon 6, and the double bond opens up there. So that's the second enolate can do that as the next step, because once the enolate is formed, it attacks the electrophile. And for the third enolate, the double bond comes down, and the lone pair comes down, and the double bond goes and attacks carbon 2, because that is the possibility for our enolate. So when we look at these enolates now and their attacks, let's look at what we make. I'm going to make some room here. Let's look at what are we going to make. What would be the next structure or the next intermediate that we make here. So based on this attack here, and this is why the numbering helps, because what is happening here is carbon 1, which is nucleophilic, is attacking carbon 6. So 1 attacks 6. That means we are making a 6-membered ring. So I'm going to say we have 1 here, 2, 3, 4, 5, and we have 6. Carbon 1 has attacked carbon 6, and on 6 there should be an alkoxide. We've got an oxygen with a negative charge. 6 also has a hydrogen. It's not important to draw that out because we're working with bond line structures. But that's the intermediate, the next intermediate that we're going to get. This is a 6-membered ring. Okay, so we've made a ring that's 6 carbons or 6 atoms in size. When for the second enolate, carbon 3 is nucleophilic. That's attacking carbon 6. So if we think about that, we're going to have carbon 3 attack carbon 6. So carbon 3 attacks carbon 6. So we have 3, 4, 5, and 6. On 6, we should have the alkoxide, and we have a hydrogen on 6. And on 3, we should have 2 with a double bond and carbon 1. So that's the structure that we're going to get. So what we're looking at here is a 4-membered ring. Okay, so that's what's going to happen with enolate 2. With enolate 3, carbon 5 is attacking carbon 2. So 5, 4, 3, 2, that's also a 4-membered ring. So we've got 5 connected to 2. So there's 5, here's 2. And so we have 4 and 3. And on 5, we should have carbon 6, which is an aldehyde group. And on 2, we should have an alkoxide. And on 2, we should have a methyl group, which is going to be carbon 1. So those are all the intermediates that we get. And notice this is again a 4-member ring. Now, what we know from previous discussions on the stabilities and the strains associated with rings is that 4-membered rings are much less stable, or they're more strained. Okay, so 4-membered rings, these are more strained than 6-membered rings. And so what happens in this case is, although there is a possibility for 3 enolates to form, only one of the enolates, which is enolate 1, will give you an intermediate that's more stable. So this 6-member intermediate that we're making, this is more stable compared to the other 4-membered intermediates that we make. And so what that means is thermodynamically, the reaction favors this pathway that leads to the formation of that 6-membered intermediate. And that's what proceeds to get you to the final product. Okay, so that's what happens under these conditions. So we can basically eliminate all of these other enolates and other intermediates that we've drawn here. So these do not, they don't happen, or they're not thermodynamically favorable. So it doesn't work. And so essentially what we get is we get that 6-membered ring. We don't have these enolates form, but they don't get you productive intermediates, or they're not making favorable intermediates for you. So it's only the first enolate that can give you a stable ring, like a 6-membered ring. And once this ring is formed, like all other aldol reactions, this intermediate can get protonated. It will abstract a proton from the solvent, and that would give us double bond O. This is 6, and this has a hydroxyl group now. And plus, we will have hydroxide from the water. Now, I'm not drawing out that hydrogen, which was there on carbon number 6. Okay, so we have 1, 2, 3, 4, 5, and 6. So this compound here, if you think about it, this is the beta hydroxy ketone that is formed here. Because with respect to that carbonyl group, this is alpha and this is beta. So we've made the beta hydroxy ketone. And then under the reaction conditions, the hydroxy or the hydroxide or the base can deprotonate another one of these alpha hydrogens, and that would give us a new enolate. Double bond O, negative charge, hydroxide here, so that's alpha, this is beta, and then the E1CV step happens, the hydroxide is kicked up, and that basically pushes this whole reaction forward, and it gives us the alpha beta unsaturated compound, which is what we observe there. So that's the aldol addition and the aldol condensation reaction here. Now, it does not have to be this particular molecule. We can look at other molecules, and in every case, you basically try to identify what is the most stable intermediate that is feasible. So let's say if we were not working with this starting material, let's look at another example. We'll not work through a mechanism over here, but I'm going to draw another example for you. So if we work with an intermediate where we have the carbonyl group, and we have 1, 2, 3, 4, 5, and 6. So again, we have a compound that's a diketone. There are 2 ketone groups in this molecule. When this compound is reacted with a base, with heat, again, there are several enolates that are possible here, but this compound now also has some symmetry to it, so that cuts down on the number of alpha carbons, okay? But we have alpha carbon here, this is alpha, and that's alpha. But recognize that 3 and 4 are identical, so these are both alpha primes, and 1 and 6 are identical, so they're both alphas. So we only have 2 alpha carbons here because of symmetry in the molecule. But when this compound undergoes an aldol condensation, the product that you're going to get is going to be this molecule here. So it will be alpha and beta, alpha beta unsaturated carbonyl compound. So that will be the alpha beta unsaturated carbonyl compound that you make for this particular molecule. And essentially this compound, when you work through the mechanism, you're going to get this compound by enolate formation at either 1 or 6, which are identical. So enolate formation at 1, followed by attack at carbon 5. Or if it is 6, then attack on carbon 2. So when you follow through the mechanism there, you're going to get to that alpha beta unsaturated compound. So I hope you find this discussion useful. It is complicated. There are several enolates possible, but the stability of the intermediate actually drives the reaction, or like helps you select the pathway that would take you to the product.